In the previous segment, we talked about modular inversion, and we said that Euclid's algorithm gives us an efficient way to find the inverse of an element modulo n. In this segment, we're going to forward through time, and we're going to move to the 17th and 18th century, and we're going to talk about Fermat's and Euler's contributions. Before that, let's do a quick review of what we discussed in the previous segment. So as usual, I'm going to let n denote a positive integer, and let's just say that n happens to be an n-bit integer. In other words, it's between 2 to the n and 2 to the n plus 1. As usual, we're going to let p denote a prime. Now we said that z sub n is the set of integers from 0 to n minus 1, and we said that we can add and multiply elements in the set modulo n. We also said that zn star is basically the set of invertible elements in zn, and we proved a simple lemma to say that x is invertible if and only if x is relatively prime to n. And not only did we completely understand which elements are invertible and which aren't, we also showed a very efficient algorithm based on Euclid's extended algorithm to find the inverse of an element x in Zn. And we said that the running time of this algorithm is basically order n squared, where again n is the number of bits of the number capital N. So as I said, now we're going to move from Greek times all the way to the 17th century and talk about Fermat. So Fermat stated a number of important theorems. The one that I want to show you here says the following. So suppose I give you a prime p, then in fact for any element x in zp star, it so happens that if I look at x and raise it to the power of p minus 1, I'm going to get 1 in zp. So let's look at a quick example. Suppose I set the number p to be 5, and I look at 3 to the power of p minus 1, in other words 3 to the power of 4. 3 to the power of 4 is 81, which in fact is 1 modulo 5. This example satisfies Fermat's theorem. Interestingly, Fermat actually didn't prove this theorem himself. The proof actually waited until Euler, who proved it almost 100 years later, and in fact he proved a much more general version of this theorem. So let's look at a simple application of Fermat's theorem. Suppose I look at an element x in zp star, and I want to remind you here that p must be a prime. Well, then what do we know? We know that x to the p minus 1 is equal to 1. Well, we can write x to the p minus 1 as x times x to the power of p minus 2. Well, so now we know that x times x to the power of p minus 2 happens to be equal to 1. And what that says is that really the inverse of x modulo p is simply x to the p minus 2. So this gives us another algorithm for finding the inverse of x modulo a prime. Simply raise x to the power of p minus 2, and that will give us the inverse of x. It turns out, actually, this is a fine way to compute inverses modulo a prime, but it has two deficiencies compared to Euclid's algorithm. First of all, it only works modulo primes, whereas Euclid's algorithm worked modulo composites as well. And second of all, it turns out this algorithm is actually less efficient. When we talk about how to do modular exponentiations, we're going to do that in the last segment in this module, you'll see that the running time to compute this exponentiation is actually cubic in the size of p. So this will take roughly log cube of p, whereas if you remember, Euclid's algorithm was able to compute the inverse in quadratic time in the representation of p. So not only is this algorithm less general, it only works for primes, it's also less efficient. So score 1 for Euclid, but nevertheless, this fact about primes is extremely important, and we're going to be making extensive use of it in the next couple of weeks. So let me show you a quick and simple application of Fermat's theorem. Suppose we wanted to generate a large random prime. Say our prime needed to be 1,000 bits or so. So the prime we're looking for is on the order of 2 to the 1,024, say. So here's a very simple probabilistic algorithm. What we would do is we would choose a random integer in the interval that was specified, and then we would test whether this integer satisfies Fermat's theorem. In other words, we would test, for example, using the base 2, we would test whether 2 to the power of p minus 1 equals 1 in zp. If the answer is no, then if this equality doesn't hold, then we know for sure that the number p that we chose is not a prime. And if that happens, all we do is we go back to step 1 and we try another prime. And we do this again and again and again until finally we find an integer that satisfies this condition. And once we find an integer that satisfies this condition, we simply output it and stop. Now, it turns out, this is actually a fairly difficult statement to prove, but it turns out if a random number passes this test, then it's extremely likely to be a prime. In particular, the probability that p is not a prime is very small. It's like less than 2 to the minus 60 for the range of 1024-bit numbers. As the number gets bigger and bigger, the probability that it passes this test here but is not a prime drops to 0 very quickly. So this is actually quite an interesting algorithm. You realize we're not guaranteed that the output is in fact a prime. All we know is that it's very, very likely to be a prime. In other words, the only way that it's not a prime is that we got extremely unlucky. In fact, so unlucky that a negligible probability event just happened. Another way to say this is that if you look at the set of all 1024-bit integers, then, well, there's the set of primes. Let me write prime here. And then there's a small number of composites that actually will falsify the test. Let's call them F for false primes. Let's call them FP for false primes. There's a very small number of composites that are not prime and yet will pass this test. But as we choose random integers, you know, we choose one here, one here, one here, and so on. As we choose random integers, the probability that we fall into the set of false primes is so small that it's essentially a negligible event that we can ignore. In other words, one can prove that the set of false primes is extremely small and a random choice is unlikely to pick such a false prime. Now, I should mention, in fact, this is a very simple algorithm for generating primes. It's actually by far not the best algorithm. We have much better algorithms now. And in fact, once you have a candidate prime, we now have very efficient algorithms that will actually prove beyond a doubt that this candidate prime really is a prime. So we don't even have to rely on probabilistic statements. And nevertheless, this Fermat test is so simple that I just wanted to show you that it's an easy way to generate primes, although in reality, this is not how primes are generated. As a last point, I'll say that you might be wondering how many times this iteration has to repeat until we actually find a prime. And that's actually a classic result. It's called the prime number theorem, which says that after a few hundred iterations, in fact, we'll find a prime with high probability. So in expectation, one would expect a few hundred iterations and no more. Now that we understand Fermat's theorem, the next thing I want to talk about is what's called the structure of ZP star. So here we're going to move 100 years into the future, into the 18th century, and look at the work of Euler. And one of the first things Euler showed is, in modern language, is that ZP star is what's called a cyclic group. So what does it mean that ZP star is a cyclic group? What it means is there exists some element G in ZP star, such that if we take G and raise it to a bunch of powers, G, G squared, G cubed, G to the fourth, and so on and so forth, up until we reach G to the P minus 2, notice there's no point going beyond G to the P minus 2, because G to the P minus 1 by Fermat's theorem is equal to 1. So then we will cycle back to 1. If we go back to G to the P minus 1, then G to the P will be equal to G, G to the P plus 1 will be equal to G squared, and so on and so forth. So we'll actually get a cycle if we keep raising to higher and higher powers of G. So we might as well stop at the power of G to the P minus 2. And what Euler showed is that in fact there is an element G such that if you look at all of its powers span the entire group ZP star. The powers of G give us all the elements in ZP star. An element of this type is called a generator. So G would be said to be a generator of ZP star. So let's look at a quick example. So let's look, for example, at P equals 7, and let's look at all the powers of 3. So 3 squared, 3 cubed, 3 to the 4th, 3 to the 5th. 3 to the 6th, already we know, is equal to 1 modulo 7 by Fermat's theorem. So there's no point in looking at 3 to the 6th. We know we would just get 1. So here I calculated all these powers for you and I wrote them out. And you see that in fact we get all the numbers in Z7 stars. In other words, we get 1, 2, 3, 4, 5, and 6. So we would say that 3 is a generator of Z7 star. Now I should point out that not every element is a generator. For example, if we look at all the powers of 2, well, that's not going to generate the entire group. In particular, if we look at 2 to the 0, we get 1. 2 to the 1, we get 2. 2 squared is 4, and 2 cubed is 8, which is 1 modulo 7. So we cycled back, and then 2 to the 4th would be 2, 2 to the 5th would be 4, and so on and so forth. So if we look at the powers of 2, we just get 1, 2, and 4. We don't get the whole group, and therefore we say that 2 is not a generator of Z7 star. Now again, something that we'll use very often is given an element G of ZP star, if we look at the set of all powers of G, the resulting set is going to be called the group generated by G. Okay, so these are all the powers of G. They give us what's called a multiplicative group. Again, the technical term doesn't matter. The point is we're going to call all these powers of G the group generated by G. In fact, there's this notation which I won't use very often, angle G angle, to denote this group that's generated by G. And then we call the order of G in ZP star, we simply let that be the size of the group that's generated by G. So in other words, the order of G in ZP star is the size of this group, but another way to think about that is basically it's the smallest integer a such that G to the a is equal to 1 in ZP. Okay, it's basically the smallest power that causes a power of G to be equal to 1. And it's very easy to see that this equality here, basically if we look at all the powers of G, then we look at 1, G, G squared, G cubed, and so on and so forth, up until we get to the G to the order of G minus 1. And then if we look at the order of at G to the order of G, this thing is simply going to be equal to 1 by definition. Okay, so there's no point in looking at any higher powers. We might as well just stop raising 2 powers here. And as a result, the size of the set, in fact, is the order of G. And you can see that the order is the smallest power such that raising G to that power gives us 1 in ZP. So I hope this is clear, although it might take a little bit of thinking to absorb all this notation. But in the meantime, let's look at a few examples. So again, let's fix our prime to be 7. And let's look at the order of a number of elements. So what is the order of 3 modulo 7? Well, we're asking what is the size of the group that 3 generates modulo 7? Well, we said that 3 is a generator of Z7 star, so it generates all of Z7 star. There are 6 elements in Z7 star, and therefore we say that the order of 3 is equal to 6. Similarly, I can ask, well, what is the order of 2 modulo 7? And in fact, we already saw the answer. So I'll ask you, what is the order of 2 modulo 7, and see if you can figure out what this answer is. So the answer is 3, and again, the reason is, if we look at the set of powers of 2 modulo 7, well, we have 1, 2, 2 squared, and then 2 cubed is already equal to 1. So this is the entire set of powers of 2 modulo 7. There are only 3 of them, and therefore the order of 2 modulo 7 is exactly 3. Now let me ask you a trick question. What's the order of 1 modulo 7? Well, the answer is 1, because if you look at the group that's generated by 1, well, there's only one number in that group, namely the number 1. If I raise 1 to a whole bunch of powers, I'm always going to get 1, and therefore the order of 1 modulo 7, in fact the order of 1 modulo any prime, is always going to be 1. Now there's an important theorem of Lagrange that, actually this is a very, very special case of it, what I'm stating here, but Lagrange's theorem basically implies that if you look at the order of G modulo P, the order is always going to divide P minus 1. So in our 2 example, you see 6 divides 7 minus 1, 6 divides 6, and similarly 3 divides 7 minus 1, namely again 3 divides 6. But this is very general. The order is always going to be a factor of P minus 1. In fact, I'll tell you, maybe as a puzzle for you to think about, it's actually very easy to deduce Fermat's theorem directly from this fact, from this Lagrange's theorem fact. And so Fermat's theorem really, in some sense, follows directly from Lagrange's theorem. Lagrange, by the way, did his work in the 19th century, so you can already see how we're making progress through time. We started in Greek times, and already we ended up in the 19th century. And I can tell you that more advanced crypto actually uses 20th century math very extensively. Now that we understand the structure of ZP star, let's generalize that to composites and look at the structure of Zn star. So what I want to show you here is what's called Euler's theorem, which is a direct generalization of Fermat's theorem. So Euler defined the following function. So given an integer n, he defined what's called the phi function, phi of n, to be basically the size of the set Zn star. This is sometimes called Euler's phi function, the size of the set Zn star. So for example, we already looked at Z12 star. We said that Z12 star contains these 4 elements, 1, 5, 7, and 11. and therefore we say that phi of 12 is simply the number 4. So let me ask you as a puzzle, what is phi of p? It'll basically be the size of zp star. And so in fact we said that zp star contains all of zp except for the number 0, and therefore phi of p for any prime p is going to be p minus 1. Now there's a special case which I'm going to state here and we're going to use later for the RSA system. If n happens to be a product of two primes, then phi of n is simply n minus p minus q plus 1. Now let me just show you why that's true. So basically n is the size of zn, and now we need to remove all the elements that are not relatively prime to n. Well, how can an element not be relatively prime to n? It's got to be divisible by p, or it's got to be divisible by q. Well, how many elements between 0 and n minus 1 are there that are divisible by p? Well, there are exactly q of them. How many elements are there that are divisible by q? Well, there are exactly p of them. So we subtract p to get rid of those divisible by q. We subtract q to get rid of those divisible by p. And you notice we subtracted 0 twice, because 0 is divisible both by p and q, and therefore we add 1 just to make sure we subtract 0 only once. And so it's not difficult to see that phi of n is n minus p minus q plus 1, and another way of writing that is simply p minus 1 times q minus 1. Okay, so this is a fact that we will use later on when we come back and talk about the RSA system. So far, this is just defining this phi function of Euler, but now Euler put this phi function to really good use. And what he proved is this amazing fact here that basically says that if you give me any element x in Zn star, in fact, it so happens that x to the power of phi of n is equal to 1 in Zn. So you can see that this is a generalization of Fermat's theorem. In particular, Fermat's theorem only applied to primes. For primes, we know that phi of p is equal to p minus 1. And in other words, if n were prime, we would simply write p minus 1 here, and then we would get exactly Fermat's theorem. The beauty of Euler's theorem is it applies to composites and not just primes. So let's look at some examples. So let's look at 5 to the power of phi of 12. So 5 is an element of Z12 star. If we raise it to the power of phi of 12, we should be getting 1. Well, we know that phi of 12 is 4, so we're raising 5 to the power of 4. 5 to the power of 4 is 625, and it's a simple calculation to show that that's equal to 1 modulo 12. So this is proof by example, but of course it's not a proof at all, it's just an example. But in fact, it's not difficult to prove Euler's theorem, and in fact, I'll tell you that Euler's theorem is also a very special case of Lagrange's general theorem. Okay, so we said that this is a generalization of Fermat's theorem, and in fact, as we'll see, this Euler's theorem is the basis of the RSA crypto system. So I'll stop here and we'll continue with modular quadratic equations in the next segment.